So as you know, any type of transport infrastructures, including pavement, rail track, bridges, and tunnels, are deforming under the loads, especially under the traffic loads. And deformation is a key factor to make sure the safe and efficient performance of the structures. Because before operating any highway infrastructure, we need to make sure that this structure is properly working and safely working. So before opening any road or any infrastructure, and also during the operation of infrastructure, this deformation factor should be continuously monitored. That gives this assurance to the authorities that this structure is working well and safely. So in this study, our objective is to develop an efficient and optimal method, because optimal method to measure the deformation of such these infrastructures. And that's why we are looking for an optimal and efficient way to do it. So far, various types of methods have been developed to do this issue, to do this, to get this goal. There are two main methods: contact-based and non-contact-based methods. Contact-based methods might include dial gauge or strain gauge, LVDTs, accelerometers, wire displacement sensors, each of which has its own pros and cons. And non-contact based methods also includes GPS, LiDAR, and vision-based methods. Generally, the non-contact based methods, because they are remotely monitoring the infrastructure's deformation, they are superior compared with the contact-based methods. Among the non-contact-based methods, GPS has less accuracy compared with others. And LiDAR is also a good way and is an accurate method, but it is more expensive than others. And also the other deficiency of LiDAR is that it can measure or it can monitor the infrastructure from far distances. Like it should be located far from the structure so that it could detect and make the point cloud of the structure. But the vision-based method, which is accurate like LiDAR, and also the advantage of vision-based method is that it is less expensive and it can detect the object from close distances. And also it is accurate enough. And the installation time is also efficient. It takes less time to install the experiment. So generally the non-contact based methods are more optimal than the contact-based method. Contact-based, if I want to mention some disadvantage of contact-based method, I can say these methods uses high volume of instruments and they are interrupting the traffic flow, and so the traffic flow should be stopped, and then install the equipment and measure and then collect the data and then open the road. So that is the disadvantage of these methods. But they are actually mostly, at the moment, they are mostly used in the industry because they are reliable and accurate and already tested in the field. But the right side methods like non-contact based method is still improving, still under research process. So in this study, we have used the vision-based methods, and we have investigated the performance of different methods, 2 different methods, to test it in this case. Here is the general diagram of our methodology. This methodology has 3 different sections. In the first section, we have the calibration method here, as you see. We use two types of configuration in this study. The first one is a single configuration, single camera configuration, and the other one is dual camera configuration. So we have used two types of calibration, like single camera calibration and dual camera calibration, to finalize this section. So after the first section, we have the image processing section. We have used various types of image processing algorithms to detect the target and the scene. And finally, we have the target tracking method, like 2D and 3D target tracking algorithm. So totally, we have 3 stages here to measure the deformation using region-based deformation measurement system. As you see here, the image processing method includes various stages: canny edge detection, ROI function, application, hole filling algorithm, area opening function, and region property function. So after this stage, for each of 2D and 3D deformation measurement, we have to follow different instructions. And finally, get the deformation and estimate the deformation of the structure. Okay, to validate and test our proposed methodology, we have conducted 2 different experiments. The first one has been done on the concrete beam. As you see at the top of the slide here, we have shown the sample, the concrete beam sample, and also the experiment configuration in the left side. And you see we have used the industrial camera, the IDS camera in this case, which has like 70 frames per second, which has a frame rate of 70 frames per second. So, and in the second experiment, we have a bridge model. That is the steel bridge model. As you see the arc bridge here in the scene, the picture. And we have used the high-speed camera here with the frame rate of 1000 FPS. And you can see the measurement area in this experiment as well. So in the first experiment, in the concrete beam, we have used 4 targets, as you see in the top right picture: K1, K2, K3, and K4. While in the second experiment, we have used 14 targets installed on the lateral side of the steel girder. So you see it's from P1 to P14 installed on the surface of the measurement area defined by this yellow rectangle. We are going to define different scenarios. According to these 2 experiments, we have defined 4 scenarios to be investigated in this study, which is explained in the next slide. So in this table, you can see different scenarios we have defined in this study. The first scenario, in the first and second scenario, we have used the industrial camera, IDS camera, to measure the static deformation. We have a concrete beam structure using industrial camera, measure vertical deformation, and have 2 types of camera configuration, including dual camera configuration and single camera configuration, which is equal to 3D optical, which is called 3D optical and 2D optical methods, respectively. And in the 2 next couple of scenarios, we will measure the dynamic deformation of the arc steel bridge model using a high-speed camera. So in this case, we will use again the vertical deformation using dual camera and single camera configuration. So here I'm going to talk about the, as you have seen in the methodology, I mentioned that we have three different sections. The first section is camera calibration. That is done by the camera MATLAB camera calibration toolbox. That is not very difficult to do. But at the next stage, we have to use the image processing algorithms to first detect the target point on the image. Here is the example of image processing algorithm actually that is run by the MATLAB software. As you see in the first image, this is the first image, the raw image we have taken from the concrete beam, and is ready to be analyzed. This is the gray image actually. And you can see the target. We have we have selected the top target to be detected. So here you see the target we are going to detect. In the stage 1, we have used the canny edge detection. That you see the picture is changed. You see the changing condition compared with the first image. So using canny edge detection, we are able to detect the boundary of objects, as you see here in stage 1. After this stage, we'll use the ROI function to define the boundary of the target, to detect the boundary of target of interest, as you see here. Just so in the second stage, you can see all the other objects removed and only the object, the circular target, and also some surrounding you see objects has remained. In the third stage, we will actually fill the target using the whole filling function, and then we will be more close to the target detection. And then in the next stage, we will actually remove the non-related objects using the area opening function. And in the final stage, we will be able to estimate the exact 2D pixel position of circular target using region property function. As you see here, the X and Y position, pixel position of the target is estimated relative to the image coordinate system. So in the same manner, we will analyze and we will process the image captured by the high-speed camera in bridge model experiment. As you see, I actually showed the picture at the left bottom of the slide, but the same procedure is applied to detect any of these targets in the image. So after by estimating the 2D position, pixel position of the targets, we are able to track every target in the image using target tracking algorithm, as I mentioned in the methodology in the third section. So again, in each experiment, we apply both 2D and 3D optical image-based methods to measure the static and dynamic deformation in both concrete beam and bridge model experiment. So here is the results. As you see here, in the first experiment, we just had the static deformation. So you see in the left, for example, in the left top diagram, we can see the black line, which is the true value of deformation measured by the actuator of the MTS machine, which is a true value. And the green line is the measurement result of 2D obtained by 2D optical image-based method. So as you see, it's quite, they agree with each other. And also in the right side, right top side, you can see the comparison results of the formation using MTS machine actuator and 3D optical image-based method. This shows a good agreement between these two methods. In the second experiment, the bridge model experiment, also you can see the dynamic measurement of the formation at the bottom side. So again, the green line is for the green and red line is for the optical image-based method, and the black line was obtained using wire displacement sensor. So they also shows a good agreement between these two methods. To estimate the accuracy of our methodology, we have used the normal root mean square error to compare the accuracy of our results. So as you see here, the NRMSE RMSE for 3D optical method in both experiments was found less compared with 2D optical image-based method. So we have found that 3D optical image-based method is more accurate than 2D optical image-based method in both of experiments. To finalize my presentation, we can conclude that we have actually showed the accuracy and successful performance of both proposed method, 2D and 3D optical measurement method. And also, as you see, 3D optical measurement method was found more accurate than 2D optical measurement method. The other advantage of, and we have also compared different types of cameras in this study. This is one of the main contributions of our study, that we have the industrial camera with less frame rate and high-speed camera with high frame rate. We have compared their performance with each other. As you saw, the industrial camera was more accurate. The results of industrial camera was more accurate, obtained by the results of high-speed camera. In addition, less cost, less installation time, and more convenient data acquisition procedure are the advantage of industrial cameras compared with high-speed cameras. However, if the vibration frequency of the structure is higher than normal, and we couldn't get it by using the industrial camera, we have to use the high-speed camera in this case, because we have no way to use a camera with less, with the frequency, with the frame rate less than the frequency, vibration frequency of the structure. So selecting the appropriate camera directly depends on the condition of the structure and the vibration frequency of the structure that can affect our selection procedure. And also, dual camera configuration, as you saw, was found more accurate to measure both static and dynamic deformation compared with single camera configuration. On the other hand, the single camera configuration takes less time, less cost, and is more convenient. But however, the dual camera configuration can give us more capabilities. Like we can measure the 3D deformation, but in single camera configuration, we will be able to only measure the 2D deformation.